which I'm going to present, Ensemble Distillation for Robust Model Fusion in Federated Learning, kind of gives a different approach about like how the training is performed. Like well, I mean, I like this place because it's a practical reading group, so I will try to be practical. Yeah, but my computer is not practical enough. Got it. Okay. Yes. So in a nutshell, this paper addresses the core problem of federated learning is that, you cannot just do like a FedAVG does, like putting together multiple models which are the same model, because it doesn't work in heterogeneous scenarios, and it's kind of hard to work with this sort of, let's say, labeled data that need to be kind of somehow shared and classified in a uniform way across machines and users. And it introduces a new approach, which is this ensemble distillation for model fusion, which basically means that central classifier trains a shared model by using unlabeled data, and basically makes the model behave in the same way with respect to this kind of unlabeled data, which could be like one data set which is public, or it could be generated by a GAN generator, et cetera, et cetera. So basically there is no privacy risk because you don't really need to have a shared kind of data set that users need to provide to you, and allows flexible aggregation across different like models, like bigger, smaller, different approaches. So it could be like basically from cell phones to large computers that are participating in a federated way to the training process. So this was the paper. Thank you very much. No, I'm joking. It's actually the premise, but I think like it's always nice to clarify why the paper is interesting and why it was chosen. I have to thank for like the help with the slides my prospective PhD student who is going to start with us next year, and this was basically the paper that we used to test students. So I heard it presented a number of times before, and I am now trying to do it my way for this exercise. But basically, this is the story on why we got this paper and how I kind of made the slides. So thank you, Hamad, for the unwitting help, I would say. So I will not dwell a long time on the problem of federated learning. We kind of heard it before a fair amount of times. Basically, every round the server chooses a subset of the nodes participating in the scheme, sends them a model, then the kind of clients perform their training based on their local data, and then they send it up back to the server. The server kind of puts the model together by kind of weighting like the number of data points for each model and basically averaging based on these weights. So this is the basic scheme of federated learning that everybody knows, and which is called the FedAVG. Basically, you take models which need to be structurally like the kind of same architecture, same size, et cetera, you basically superpose them and just perform a sort of algebraic operation on it, and you use whatever you get from the process to basically classify things at the clients once it's given back to them. Of course, this doesn't work in heterogeneous scenarios. You may have different model architectures, like from shuffle nets, mobile nets, res nets, et cetera, numbers of layers, quantization. It could be something that is supposed to run on a cell phone, on a desktop PC, on cars or whatever. So the interesting thing about this approach, which is called FDF, is that it will help kind of put together many models, so many shapes and complexities, and basically use some of the input from each of these models to train the final kind of model, which we will learn that actually is not a model as such, but there will be many model prototypes which are kind of trained jointly with this distillation approach. And distillation is what is the core of this approach. Basically, it is about making a student model, which is like with a certain architecture, behave like one or more teacher models, by having this sort of repeated rounds of training guided by a loss function that allow the student model basically to learn to replicate what the teacher does with like a process which is called knowledge distillation. So why is averaging not good enough when it works? So when it works, averaging basically takes individual models and gets an average. So if you see, and I'm not sure I can have a pointer, but oh yes, a pointer here. A local model here, which is trained based on local data on node 0, and then local model 1, which is trained based on local data on node 1. Get averaged, you get this sort of areas in which you have some sort of not very defined confines of the regions. The colors are overlapping, and there is no kind of strong certainty for where things should be categorized. Whereas by basically taking the models separately and like ensembling them, so basically getting to a sort of result based on the majority decision on what the outcome should be, you get very well defined regions, and you are able to classify properly. FedDF creates one model from the ensemble like input into the distillation process, which conserves many of the good things about the ensemble model, and yet it's a single model. So this is basically the interest and the power of this approach. This is on a very simple case with 2 classes, and I think a very simple model architecture, but this works also for more complicated cases. So what is at the core of this method? The basic algorithm here is shown for the case of, let's say, uniform models in the system. Basically, we have for each communication round, so the server basically performs a round by interrogating a subset of k clients, like C fraction. For each client, the client makes an update by training locally with like some sort of batch based like optimization the model. And then the model is sent to the server, and the server initializes it for model fusion. Basically, it does sort of average it and put it there. And then for n rounds of distillation, we basically sample a mini batch D from this local source of data, which could be a sort of a generated distribution or a data set like CIFAR 10 or CIFAR 100 or like ImageNet, etc., etc. And we use the ensemble output of the student, of the kind of client models, which are the teachers, to update the server student through this loss function, which I'm going to present in the next slide, which is called the average logits. And then the model is basically updated, and basically the procedure is repeated for the next round.
I'm sorry, Fabio, bear with me. I don't understand. I didn't understand where these samples D come from.
So they exist on the server. They are basically sampled from an unlabeled data set. Could be like any image data set. It is not important that they are labeled, because you are just getting the output from the let's say client models. So you basically try to use this model with the data from this data set, which is completely unrelated.
Okay.
And you want the model on the server, which you initialized at the previous step, like here, as the average of the models obtained by the clients. You basically train this student model to kind of respond to this data set, which is completely unrelated, in the same way as the kind of ensemble of the models of the clients would do. So basically, you use this average logits, which is not in the next slide, but in the one after, to give the inputs for the distillation process for the student model on the server, based on data which is local and which has nothing to do with the data on which the clients were trained.
And the step before, it's regular update. So the client has labels to update to the local model and sends the update.
The client update, I don't have it in the slides, but it's algorithm 2 on the paper. Basically, it does the kind of usual thing that clients do in this.
Okay. Okay. Thanks. Now it's clear. Thank you.
Data from your local distribution, you train a local model with Adam or with another optimizer to provide like the best possible thing, and then when it's converged on local training rounds, and we will see later what the effect of local training rounds is. Basically, you send it to the server, and the server starts here, gets the models, averages them. This is the starting student for the models.
Clear. Okay. Thank you.
You're welcome. So basically, we said that the heterogeneous scenarios were very important. How do you turn this homogeneous kind of process in which models get averaged to make the original student to a heterogeneous, let's say, friendly process? Basically, you make prototypes for every type of model in the system. So here, prototypes are marked as P. And these model prototypes are the kind of global model, but there is no actual central model. So there is no attempt to basically build one model, which is the real model and which works for everyone, and then turn it into like some sort of heterogeneous version by kind of quantizing or like distilling the model into something else. Here, basically, distillation is the process by which a number of prototype models get distilled at the same time from all the inputs from the clients. And I think this is a powerful idea. Also, we remarked that, as I said before, the distillation on the server uses a separate unlabeled data set, which could be basically even generated by a GAN generator seeded with I don't know, well-known image data sets. So it is quite crafty because it maintains the same privacy properties of federated learning. The server doesn't know anything about the data, anything. And there is no central model, so there is this kind of ensemble of different architectures that can get trained in parallel together to basically mimic the behavior of an ensemble of clients of any architecture. So this is why this paper is a bit, let's say, interesting, and I wanted to submit it to your attention. We mentioned average logits, which is basically the way by which the student on the server gets trained to approximate the behavior of an ensemble of models from the clients. D in this picture is the samples from the local model on the server. Basically, we take the output of the model on the server here. We take the averaged output of the kind of students, of the models from the clients who are the teachers on the server. We apply the sigma function, which is basically, I don't know if my animations work. They don't. Perfect. Do I get an animation to run? Okay. So basically, we have the sigma, which is the softmax function, which basically smooths over the output of their content. And we calculate the Kullback-Leibler divergence, and basically we use this sort of divergence to guide the convergence of the training of the student model on the server. So basically, this works on data which has nothing to do with original data distribution, and make sure that models behave in a similar way. We will see what happens when we pick different distributions of different data sets to this process. Like the spoiler is that it works very well with most structured data, and it just fails horribly with random data. And this is quite interesting, I think, as a general consideration. So if there are no questions on this slide, I will move forward with basically the architecture of this sort of distillation process. The blue squares are like the different prototypes. So there are different categories of clients with different models, could be different size or architectures, whatever. And they are handled separately for the kind of generation of, let's say, prototype models at the server for the server to train. But then the server trains these various P prototypes together in a distilled way from the output of whatever client models. So this is really something that makes information coming from any type of model relevant to the rest of the models. And so it also kind of underscores another advantage of this approach. Since the fusion happens on the server, like the clients have no additional overhead, they don't really have to turn like whatever server model into something usable locally at the expense of additional computation. So this seems to be a very clever idea. The paper proposes an evaluation. So this architecture uses in different stages ResNet, VGG, ShuffleNet, and DistillBird on different datasets, Cypher 10 or 100, and ImageNet and NLP datasets, which I'm not very familiar with. And it kind of also includes analysis in heterogeneous data distribution scenarios with the usual Dirichlet distribution control of heterogeneity of data distributions. From the main table, there is a comparison of this method, which is called FDF, to FedAVG and other similar methods that are based on average of models, and the striking result is the speed of convergence in terms of communication rounds across various sampling rates and heterogeneity in the data. So this table kind of shows that it is much more efficient to do distillation than it is to do averaging, and B, there is a definite advantage in increasing the local rounds of training by the nodes before they send their model, because you can really, let's say, improve the convergence, number of convergence rounds to get target accuracy. And basically, this number is very much lower compared to the other approaches.
Sorry, I have a question.
Yes.
So I suppose that the performance that you get depends on how many different models you get on your clients and how well distributed are the data in these models?
In this table, I think the models are uniform. And the data are distributed with Dirichlet. So the left column for each subcolumn is for alpha equal to 1. So I guess it is already a skewed distribution of data across the classes. We will see in the next picture what it looks like. And this is alpha equal to 0.1. The target is the same for all models, for all methods, sorry, like T is 80% of accuracy and 75% in the very kind of skewed scenario. So this is basically the comparison between a case where classes are more uniform and here classes are very much less uniform.
But in this way, when they do the FedDF algorithm, they use different models across different clients, or simply they use the same model across different clients, but then they average it using this distillation process.
For this comparison to be possible, like every architecture is using
the same. Okay, now it's clear. Yeah.
Or what you suggest, which is probably kind of interesting to check. It's not possible to have a FedAVG because there would be many different averages.
Yeah. This is clear. This is clear. It was a yeah. Now I see that this is the only possible comparison. But you have to bear with me today.
It's okay. Don't worry. I mean, it takes some time to understand really like the fine points of this paper. I needed to hear it presented at least like 6 or 7 times before I actually. Well, I'm not very fast, and I don't need to be. Anyways, so this is basically what I was kind of pointing out about the kind of skewness of the data across classes. So if the alpha equal to 100 is the uniform case, with alpha equal to 1, you get classes which are more or less represented. So this is probably a fairly good example of what would be like a client distribution with not too much skew. And this is basically the extreme example of clients that have a single class or two classes, or like a few elements in a very small number of classes. And in that situation, although, well, of course, it requires longer times to converge. When the sampling becomes a little bit more extensive, there is not a lot of difference in the kind of communication rounds required, and it is basically much more performing compared to federated average. And especially the kind of skewness of the data distribution has a great impact on other methods which are based on the average, which basically work well with sort of more uniform data sets. And we see that here, like the penalty is not that big, and convergence happens in a small number of rounds. So here, basically, for a fixed 40% sampling, we get the comparison between the behavior of FedAVG and FedDF, the method proposed in this paper, across the number of local training rounds on the clients. So we see that whereas for FedAVG, training basically does not increase much the performance of like the overall model. With FedDF, we get an increase, which seems to be robust across the let's say skewness of data distribution in the accuracy. So basically, by increasing the number of local epochs on the clients, so basically having the clients process more data in their kind of mini batch training of the local model, we get better overall models on the global scale. This is for like 100% of the data or 50% of the data. We see a consistent outperforming between FedDF and FedAVG for numbers of like local training rounds, which like are above say 20 in the worst possible case. So it is an effective way to utilize communication rounds if we can train more locally to obtain a better effect on the global model. There is a lengthy discussion about the effect of batch versus group normalization. So group normalization has been applied to federated learning in order to basically improve the behavior of batch normalization when the data becomes skewed. And this was probably visible in the previous table too, like with evolutions of FedAVG, which used this mechanism to improve like the behavior by kind of reconstructing groups of data which are kind of similar before doing the averaging. But FedDF outperforms with the simple batch normalization the various attempts and obtains much better results on like different data sets with different degrees of heterogeneity. So perhaps there's better ways to solve the problem, I think, is the message that this table gives. And it also works for other completely different applications. So this is basically NLP outcome. So the model uses Distillation, which I'm not familiar with because I know very little about NLP. The kind of message to take away from this plot is that whereas centralized training is the kind of target accuracy, federated learning through FedDF kind of approximates it better compared to federated learning with FedAVG. And different data sets. This is AG News, and this one is SST2, have a kind of different kind of levels of performance, but FedDF works better. And I guess this is what this plot shows. This is more complicated. The paper kind of contains like this upper bound in the performance of FedDF with this basically compared to the Ensemble. The paper contains a lengthy appendix which contains a lot of plots and kind of contextualize many of the plots in the paper with more extensive kind of parameterization, etc., etc. So this is really a honest paper which is trying to basically show how things work and helping people to basically realize the strength and the weaknesses of this mechanism. The proof and the kind of explanation, which I will summarize in basically the inefficiency between the Ensemble and the kind of distillated version is due to the kind of difference in risk between the kind of client models and the kind of centralized model that has been trained from them. So this is just to say that we have a sort of target, which is the Ensemble, and with respect to that Ensemble, the local properties of the models will kind of increase the kind of performance loss. And I think almost final series of plots here shows basically federated learning on heterogeneous systems with 3 neural architectures, comparing the effects of averaging, which are the kind of large bands of the 3 colors, with the effects of distillation, which are the small bands of the 3 colors also, compared to the performance of the Ensemble model, which is kind of dominating in every case the performance of FDF. It's interesting because it says that kind of across architectures and across number of communication rounds, distillation works better than averaging. And just to finish, which is basically the very striking result of this paper about the selection of the dataset on the server to do the distillation. You may use whatever you want, basically, except random data. So in the left plot, you see the performance of Cypher or STL or ImageNet, or even generated data from a generator. They all provide more or less the same performance in terms of distillation, which is better compared to the FedAVG outcomes. Here is the result where randomized data from a fully random distribution is used. So basically random noise. And so it is interesting, random doesn't work. If you have something that resembles real data, could be kind of fake data, but kind of generated from a distribution, trained on real data, it is good. So this is good news because we don't really need any particular data set with particular labels or on the server to provide good results. And yeah, this is a key achievement of this technique. And I think it is very interesting for people who work in federated learning because it guarantees privacy. You don't need to know anything about the data basically to make this thing work. I forget what the other plots were supposed to show. Probably the evolution of accuracy, top 1 accuracy, with this many non-random data sets with respect to FedAVG, increase in the local communication rounds. We see that the increase on the accuracy of FedAVG is kind of slower and basically takes more rounds to achieve basically maximum accuracy. So this is robust to the image dataset being used. And I promise it's the last plot, and I will kind of go over it very quickly. This shows that this fusion approach is efficient with respect to data being used. Number of classes, so basically whatever number of classes of the fusion dataset on the server, the kind of performance in terms of accuracy is pretty stable. you can have a very small data set for doing this sort of distillation on the server, and you basically obtain already pretty good results with like 1% of the data. You don't need really 100% of the size of the data set. And it converts very fast. So you just like need to have a number of distillation steps, and there's little advantage to continuing distillation after a certain point. So yeah, I mean, this paper, I liked it. And I cannot say that of many papers, especially the ones that I read these days. So 4 takeaways will be that FedDF introduced a distillation framework for robust federated model fusion, works with heterogeneous clients, is robust to non-IID data, and can work with different network architectures at the same time. It outperforms FedAVG by a lot, and other distillation-based methods also. As of 2020, I think it compares already with like kind of competing models that were coming out at the same conference, and showed an edge over them. I did not dwell in the related work section, but there's probably a lot of things to be considered in things that have been happening in the literature 2020 onwards. So like perhaps there could be a reason to update this with current knowledge. I certainly will do that with my student when it comes. Ensemble distillation is very efficient, and it increases the usefulness of local training of models on clients, and allows any kind of model to contribute something to the ensemble decision. And finally, distillation happens on the server, so the clients don't really have to worry to generate a model which is adapted to the local architecture. The server does it for them by training this sort of set of models at the same time based on input from all the clients, and deployable to any selected client. So this concludes my presentation of the paper. I would be happy to address your questions.
Oh, thanks a lot. It's very nice. So maybe you take the questions in the room first, if there are any.
I think
no.
There are people from, I assure you, like
no, I know, but I don't see them because I see only you now.
I know. There are 3. There are not as lip, so I can. Plus, Chris.
So maybe from the bridge, we have questions.
Yes, maybe a small question. Hello, Fabio.
Hey, Gerard.
I really like this paper as you do, because it's not tied to a specific architecture. I mean, it can work with any new model that comes along, even in the future. So that's very good for it to stay very, I mean, to prove useful in the future, no matter what new model comes that can be used by the clients. I have one question about, did they do, especially since they published this paper, did they do some study on if you have like adversarial clients, like if you have some clients which do on purpose training of bad stuff, or like stuff that would compromise this process of federating the overall result, and like how many clients would you need to make this ensemble model perform worse for everyone?
So thanks for the question. It's quite interesting to consider this aspect. It was not contained in the paper. I think, well, for real application, of course, it is a concern. Like honesty has always been, let's say, I think, supposed as a kind of precondition of these things to be effective, because of course, whenever you're averaging or doing other things to the input, if the input is garbage, then is the output also. So I guess that, I mean, the response could be kind of looked at in this sort of kind of filtering and training criteria. If you manage to compromise the output of the softmax with models that kind of misbehave, I would suppose that you you basically skew the results and make the outcome basically bad. So I would say that here it's probably a quorum issue. If there are like multiple models that misbehave in the same way, then you would be able to misrepresent the kind of typical behavior of models in the.
This is where it's less intuitive for you, because when you do averaging, of course, it's obvious that you need a certain volume of bad clients or bad actors to influence the outcome. But here with the teacher-student approach, it's less clear to me the volume which would be required.
Yeah, my kind of expectation, which is totally uninformed, is that it is more resistant, like to the kind of small creeping perturbations that you could have by having a model that basically tries to, let's say, ruin an average, because here you need like basically every model contributes one vote to the outcome, and the softmax basically will select as a kind of the smoothed maximum, like the most prevalent answer across the different models. So looks like it would be some sort of like voting problem or kind of
so that would be another interesting feature. Okay.
This seems to be quite interesting to see how you can ruin a softmax by misbehaving, perhaps strategically, with collusion, etc. But I think this is where like the attack is played and kind of foiled. So yeah.
Thanks.
Thanks for the question.
So, are there any other questions in the room from the bridge? If not, I have one. Shoot, Andrea, shoot, go.
Yeah, actually, it's the same question as my first one, and maybe if you answered already, it's my bad connection, so I missed some words. So I created myself a conviction of what federated learning is, and so I hope you will contradict it. So what I think is that federated learning is a fascinating, useless thing that became a big thing because it was this word was created by Google. So maybe all of what I said is incorrect, but this is my impression. And it became a big thing also because it's fascinating. So it's nice to study and to say, okay, this method performs better than another. And for me, a proof of the fact that it's useless is that I don't know any practical application of it except the Google keyboard. Okay, so now maybe everything what I said is wrong. This is why I'm telling it straight, so that you can tell me, no, it's wrong. There are these practical applications. For me, the applications are very rare because you need something in which you don't want a central trusted node that can have all the data and perform training for all the data. Yeah, of course, intuitively you can say, yeah, it's nice not to have this central node, but in practice, all the complications needed for federated learning are not justified by this fact of not having the central node. I mean, I will tell a simple, I will turn the question into a simple thing. Do you know a practical application of federated learning apart from the
Google keyboard? Your voice disappeared and you're muted now. I wasn't.
Yeah. I muted just, yes. I don't know if my question was audible.
It was audible until like the Google keyboard bit that you didn't say, but I kind of predicted from like
yeah. So is there any practical application?
Well, I mean,
apart from speculative thing, yeah, because for the health maybe it's good, etc.
So
apart from this speculative.
yeah, I understand you. Like I always subject the ideas that I work on to this sort of questioning. Like, is this real? Like, what's the point? Is that a problem that I would think I have? I cannot answer you in a definitive way because I don't really have enough kind of imagination. So what is the point of doing federated learning on, say, images? Like, because you don't want to send your images to a server, you want to send like basically a model that kind of represent what you learned on your images, and then like the server wants to collect, I don't know, why. Like, I guess the question why is a question that I cannot really satisfy with my limited imagination. That it has uses like Google keyboard and other sort of practical things where people are supposed to like basically behave in the same way, but with kind of important local difference that should be preserved. There may not be like as significant problems in the wild as that one. The future,
maybe I have one, which is more, I'm falling back to the vehicular problems often, but because they are really, really tight on privacy requirements. So if you imagine that you want the help, for example, of the edge to train your models for identifying objects or situations on the road, you cannot really think about feeding your images to the edge because of privacy reasons, because this will not be acceptable from regulations point of view, because it breaches too many privacy angles. And so maybe in this context, the feasibility of a federated scheme is an enabler for collective learning. And I mean, what Tesla does is it does this by pulling all the information from their cars, and so they can train central models. But is there a way of building a model that is not a private model or a proprietary model, but it's an open model to which everybody contributes? And I think you can think about this kind of perspective only if you have the tools for doing it in a privacy preserving way. And
you're saying
then
that I mean, image classification for like a driverless vehicle is like an application that, and I agree. Like one thing that is which is concerning is the amount of images that you need to provide. Like basically with Teslas, I have cameras on continuously and transmitting via like whatever system they have for speaking home. Is that something that we want, to have a car that is kind of basically a number of cameras always on? I guess there are other things which are perhaps specific to vehicles, so perhaps some sort of inertial measurements about like things that led to accidents, or some way to anticipate malfunction by having like recording of inertial measurement units before piece failures, or like, so basically predictive maintenance of vehicles could benefit from this thing, and privacy there is probably less relevant, but in a way, like you're trying to access kind of sensitive data to some people, I guess. I don't know. I mean,
yeah, well, but
Yeah,
I agree with Andrea on the fact that it's kind of hard to imagine this deployed right now.
yeah, because image classification, okay, you need the guy driving the vehicle to classify on the fly the images. And where do you take the labels?
well,
yeah.
there are classes, and if the car has some degree of intelligence, knows what a stop sign is, etc., etc. So you can basically label some sort of image based on, and then use that to train, like to improve the performance of some sort of model. I mean, I think that a lot of effort went into like proprietary navigation systems. So I guess that generating like a kind of synthetic video of intersections with cars of different colors in different lighting conditions, etc., is something that can lead to the ability to have like either synthetic images with synthetic labels that you use for like priming, or but yeah, I mean, in a sense,
yeah, actually, you don't really need labels for those scenarios. Like if you're trying to learn how to behave when you have an image or something, a video of something happening, if the driver intervenes, that's the label. The fact that it didn't let the automatic driving happen and he intervened, then the model can learn what the driver did, and instead of what it was planning to do itself.
Yes.
And so these are the kind of labels that you get automatically and that you could get for each driver. And so if you have a model, which is not what's happening on the Tesla right now, but in the future, if you have a model which learns per driver to improve the way it drives, which I think is the way to go, because not everybody drives the same way. So probably in the future, people would like to have an automatic behavior which is more in line with what they would like. So in that scenario, yeah, it kind of makes sense, the federated learning, I guess.
Yeah.
Okay.
But you're right, Andrea, that right now, apart from the Google keyboard, I couldn't come up with a use case that works today.
So I guess it's a failure of our collective imagination then. But
No. It's it shows the power of Google, because if some of us would have come up with the same thing, everybody would have said, "Oh yeah, but this is useless."
Well, they did it
Since
with
it's Google,
nobody really kind of attempted to counter the influence of Google on the global mindset. I think it is not very nice when like a single entity, corporation, or whatever dictates what people should think, controls the standards, and tells people you should do research on that. But this is what happens when you have monopolies anyway, yeah, it is a fair point. We are discussing about federated learning. It may not be a real problem. There are interesting aspects that can be drawn from learning about it. I guess the fundamental thing is how can we kind of get many models to provide information to train a better model is warranted. Then the strict limitations about who gets to look at the data to guarantee privacy are perhaps the more, let's say, superficial part of federated learning, but they give like a better motivation for the scenario. So if we were to ignore privacy, perhaps there wouldn't be like nothing that can be salvaged from this work. So yeah, I mean, I'd like to end on a hopeful note that this is not for nothing, and at least this paper has two good contributions about distillation, which works better than averaging, and the way distillation happens that doesn't require to have any particularly kind of relevant source of data to be able to make it work.
I still have a question though. If you are okay in taking 2 more minutes and then we wrap it up. So if you go back to like your third slide or fourth slide, this one, no, the following one, with the scheme of the server, learners, student.
The FedDF or the kind?
Yeah. Go on. And this one, yes. Sorry, it was much further deep in your presentation. So my understanding of what you said today of this paper is that if I use distillation instead of averaging, even if I have the same model and architecture on all these blue boxes, because this is what they did when they did validation, I do overall better and I converge faster and everything is smoother. So my question is, why don't you use distillation also in the submodels towards the leaves, so towards the clients? Basically, my understanding is what happens in the yellow cloud at the server is standard averaging across one architecture or one model. And can you pull distillation inside that yellow cloud as well?
So the distillation happens at the level. Sorry, my battery is finishing. Fast enough. Okay, save it. Okay, so basically the server is the kind of box there.
Yeah.
And the blue kind of boxes are sets of clients that have the same architectures.
Yeah.
So, but this is a logic.
And the weight one that you have in the blue box is
so really you have every client contributing to the sort of basic server model before distillation by averaging the model about like all the clients that have the same architecture.
exactly.
So basically that's how you generate, like it's basically FedAVG to have a first model on the server to be trained through distillation. So basically you do this for all the groups of clients that have different architectures. And then you use basically all the inputs of the model from the clients to train all the architectures of models on the server via distillation. So basically distillation happens on the server and generates at the same time like P models from the output of all the selected clients. So yeah, I don't really understand your question. Like,
can you replicate this same model that you have in the server also to reach model 1 P1 and model 2 P2? Like, can you split your clients in your blue box into further clusters, and instead of basic averaging, do the distillation thing again, like in a recursive way or in a meta way?
so
I know it's a weak.
You're suggesting that the initialization of the model be created through distillation too, or?
Yeah, because what they did to validate was doing exactly this. So having the same model on all clients. This is what I understood, and then comparing what you do with averaging and what you do with distillation. And so I understand that there is some gain to be taken there, but my question was, if you do it in a recursive way, deep down until the leaves, there is still some gain you can have, or at a certain time it does stop because this is reasonable to expect, because at a certain point this operator with the Kullback-Leibler divergence will not work anymore if you do not have enough points. But yeah, it was just a thought.
I don't think it could be applied recursively, because I fail to understand like where distillation would have actually an impact in other places. So when you do distillation, basically you take a model architecture and you tell it to behave like the prevailing behavior of all the clients from whatever kind of models they may be running. So there is no other point where like you could pre-distill the thing, because, well, I mean, you are taking all the clients who have a decent model, like you give them like the equal weight, like by the softmax kind of wrapped toolbar library kind of distance the evaluation of the thing. And so if you wanted to give more or less weight, probably you would be able to do it in there, but I don't really see where this sort of recursive behavior could be required by the structure of the problem. Like, in a sense, here you're using all the input to generate in parallel a number of models with the same kind of approach. So I don't see any sort of natural subdivision in which this would make sense in turn. I
don't know if it would make sense, but to me, to my current understanding of this architecture, it would be at least possible. And the place where this would happen is inside every blue box. The blue box doesn't exist as such. It's just the set of nodes with the same architecture. So it is not a machine or so. Yeah. I know, but when you do the red clouds, they are averaging the weights. Well, it happens on the server. Yeah, I know it happens on the server. That's why. But there is no box. So if you do it on the server, it's on the server. And yeah, but can you, instead of averaging in the red cloud, do distillation? Well, and then distillation on the distilled models? What would you distill to begin with? So this basically red thing is just basically the starting point for starting the distillation. Okay, because you would need data again to do the distillation. Okay. You need okay. Realization of your model, and this is basically what the red provides. Now it becomes the model of the server once it's and then it's sent back to the. So the direction of the arrows perhaps is misleading. I did take this picture from my perspective. No, it's not. It's not. It was I mean, I was following a line of thought, but now I see because it's not. I see why it's not very correct, and so thank you. You're welcome. And thanks a lot for this paper. I think it's very interesting, and it's to me it was really new. So thank you. Thanks to your prospective student for the slides. I did work a little bit on it, like 4 or 5 hours, but he did a very good job to kind of filter many things. I had to remove a lot of slides because he really did a search for literature, etc., etc. So I hope you will give us a follow-up next year in the reading group. Yeah, I mean, the topic will be about federated learning, of course. Hopefully, it's not for nothing, Andrea. Like we hope, but I mean, there are many things to be done on the side. Much of the work that we didn't do on federated learning comes from the kind of interaction we have with INRIA and you know Giovanni, of course, and we are kind of planning to continue on this track with the side contributions if they make sense. Very welcome, of course, and perhaps collaboration at links will kind of restart with a student and some people interested in these subjects. So it's going to be good to be back. Thank you very much.
Thank you.
Thank you.
Thank you.
Have a good lunch. Bon appétit.